Let's go ahead and get started. Ooh, there we go. Let me get a little bit of a census in the room before I get started. Who here has done anything with ranges at this point? Okay, so a bunch of people. The plants in the front row, that you guys are, you're not fair. So ranges is something new in C++ 20, and it's really a fundamental redesign of the STL. And how I started looking at ranges was really a few years back. It was clear after Eric Niebler gave a presentation in C++ Now about ranges and was actively working on proposals for the standards committee that this is where things were going to go. So a few years ago at C++ Now in a library in a week, kind of out of frustration, we decided that we needed to write some example code for ranges. And after that point in time, we started using ranges in production, even though that was verboten by Mr. Niebler as well. But we decided that we would do it anyway, and so far it's been a good experience. Today I'm going to talk to you about C++ 20 ranges, and so I'm going to limit myself to the content that will be in C++ 20 as best I can do that, and I'll tell you the status of that in a bit. So we're going to go through a lot of code, and hopefully when you walk away from the talk today, you'll have a good idea about the different parts of the library and how it's structured, and how you might apply it to your own situation. Okay, so let's just start with the basics. In STL, the old way to run a sort would be something like this. I have an std array, I call sort with begin and end. All very straightforward. We all know and love this. Or maybe we don't love it so much because of that begin end. So really, at its most core level, ranges is going to give you a way to write STL code like you've wanted to write it for 2 decades now. In a clear and unambiguous way. And the 13 characters there is really not the important point. Really the important point is that there's a higher signal-to-noise ratio in this code. Here's how you might do find if the old way. Once again, you would have something like a collection, like an array. You have a predicate, and you would pass that predicate to the find if algorithm, returning an iterator. If the iterator is not end, then you can dereference it and access its value. It's pretty much the same thing in ranges, once again, except for once again the begin and end is gone. Now you're starting to see the point of the quote on the first slide. You can see that the begin and end starts to evaporate from your code. But there's something that's really much more radical about the range library. And that part of the radical change is views. And we're going to go through and define what these things are in some depth as we go through the presentation. But if you look at this particular code, you'll notice I have my same array, I have my same predicate, and now I have a for loop. I'll get to the keynote point earlier today about for loops, but in any case, you can see I have a range filter. It takes the range and it applies the predicate, and I only drop into the loop when the predicate is actually evaluated to true. Now, if you look carefully, you'll note there are no iterators. You do not see the presence of iterators in this code. You only get values in the for loop that you can access. And that's what's very radical about this. And we'll see how that's actually done. So what are the goals of this talk? I'm going to give you a lot of range code today. So you're going to see a lot of what's going to be in standard ranges in C++ 20. We'll talk about some things, how to apply it. This, even though I think I accidentally said this was an intermediate to advanced, it's probably more beginner intermediate. in that I'm not going to show you some super complicated, crazy examples for how to use range code, because reality is that 90% of your uses are going to be very straightforward and simple. And I think it's easier to see how things go together when we keep it reasonably easy. So we'll also talk about some of the other changes that go along, like projections on algorithms. We'll cover that briefly. And we'll talk about what's a range versus a view versus an adapter. Those are fundamental concepts in using this library. So here's the outline of the talk. I'm not going to dwell on it. So we're going to go through basics. We're going to go through the algorithms. We'll go through views. We'll talk a little bit about string view and span, which are view types. And then we're going to survey views, because as I said, that's the radical part of this, and some performance and observations. So things you'll see me do in this talk, I will refer to the standard in places. I am going to take questions, so this can be interactive, at least until we get behind on time. If I can't answer something right away, we'll talk about it afterward to make sure that we get through the material. Like I said, I will show you lots of code, and as far as I'm concerned, I won't show you any code that I haven't compiled somewhere. In some universe, on some compiler, with some version of ranges, which is a little harder than you might think over the last 6 months. But now it's getting easier, and I'll show you about that. So the primary environment I have, which is not for any reason other than it's easy for me, is mostly GCC and Linux. And this presentation has really been developed over the past 6 months when many things in the ranges implementations have been in flux. The standard has been in flux as the process of standardization has been happening. But now we're at a point, and I'll go through this in a minute, that the design is settled and the committee is only bug fixing. So really what I'm going to present today should stay rather stable as we go forward. So there's 3 canonical implementations. Range v3, of course, is Eric Niebler's. That's the most famous one. If you ask for ranges CPP20 namespace, that will get you the CPP20 part of the library. CMC STL2 is Casey Carter's, and you use STD experimental ranges to get the C++20 part. And then there's nano range with Tristan Brindle, who's sitting in the front row here. And really that's an independent from the specification development of ranges, which is very interesting. And quite frankly, was new. I learned about it at the conference this week, and it's really cool. So the status of this has been, as I said, in much flux. And there were many interactions between compilers, and so at times it was quite difficult to actually get this code to compile, but it is getting much better. The primary proposal that went into the standard was really adopted in 2018 in San Diego. It really had been multiple years in the making. And that was not everything. There were a series of follow-ups, including changes that went into the Cologne meeting about a month and a half ago. But as I said, we're design complete, and only bug fixes in the next year and change before the final stamp goes on C++20. So, how does it feel to use ranges now? I think we're getting close. There are still bugs in the implementations, of course. How about Godbolt? Can we use it on Godbolt? Yes, we can. Both CMC STL2 and v3 are libraries that are selectable, so you can play around with range code there. If you don't know about Godbolt, try and find Matt Godbolt. He's here somewhere. Tristan actually showed me a neat trick. You can actually pull in nano range by doing an include to the GitHub, which is awesome. How about CPP reference? Anybody use this site? Yeah. So, yeah, it doesn't quite work. They use Coloru as their backend for compilation. So they have code as examples, but it doesn't actually compile. So, your mileage may vary with that one. But overall, I'd say things are in a state where you can definitely get started, and you can definitely at least experiment with C++20 ranges. All right, so let's step back and talk about the basics. There's really 4 important things. And one of the things that's gotten really hard about giving a talk about something is you can't use the word concept anymore. Well, so there are ranges, and ranges are something that can be iterated over, but there's a multitude of different range concepts. And I'm not really going to talk about the range concepts today because of lack of time, but needless to say, in general, a range is something that can be iterated over, and we'll detail this a little bit more. A range algorithm is something that obviously an algorithm that takes a range. And a view is a lazy range that's cheap to copy. Now, you might say something about programmers and being lazy and cheap, but then you might have to endure more of my bad humor. And then there's a range adapter, which is a way to make a range into a view so that you can use a regular range as a view. And we're going to detail that a little bit more in a minute. So how does this lay out in terms of the mechanics of it? So in C++20, there'll be a new header called ranges. There'll be 3 new namespaces. There's the ranges namespace. That has both the new algorithms and the views in it. And there's a ranges sub namespace called view, which has the range adapters in it. Now, you're already thinking std : ranges : views is getting too long, which it is. So there's a shortcut to the adapter namespace called views. And so that's how you'll see most of the code written. And you'll notice that there's going to be a naming pattern here when we start looking at these. You'll see that things in std : ranges like take view turn into std : views : take. So you can already see the name difference tells you whether the thing is really an adapter or whether it's a view itself. An adapter, again, is just something that can manufacture a view. So you'll see in a lot of my talk here, I shortcut everything to RNG. I also take a lot of other shortcuts on the slides. Sometimes I show you everything, but often it's shortcutted to make it easier to see. So, why did the committee make this decision to sub namespace? Well, the primary reason is that these things, the new algorithms, are not just new overloads. They have different return types. They have some additional parameters in many cases. And anything that removes a parameter, of course, is going to break code. So really, I think there were a lot of folks on the committee that didn't want to do it this way, but it was the compromise that made the most sense for backward compatibility. So that's why it's in a different namespace. All right. So really, Jeff, what's a range? You haven't really told me what a range is yet. So an iterator pair is the most simple version. That's really the idea of a common range where the iterators are the same. But one of the things that's new in these algorithms and in the views is that the iterator type and the sentinel do not have to be the same. In other words, the end of the range can be a different type from the iterator as long as they can compare to each other. And this gives us some interesting properties now where ranges, and in particular views, can be logically infinite. Channeling Andre, we're always going to have infinite for loops and infinite ranges going forward. So let's look at some concrete examples. So clearly, collections are ranges. Strings are ranges. They're sequence containers. And many other things in the standard library are ranges. So your arrays, vectors, maps, sets list can all be ranges. The container adapters, yeah, are not ranges. And why not? Because they don't have a begin end and you cannot iterate over them. So other things like directory iterators, stream iterators, and so forth can be ranges. And then finally at the bottom, we'll talk a little bit about string view and span. So one of the most powerful things about the range design is that it leverages 20 years of C++ experience. And specifically, that begin-end semantic allows us to now apply ranges to all of the existing code in the world that has begin, end, and iterators. And it doesn't need to be modified at all. So what I have here is an example where boost flat map, which is not rangified in any way, I construct the flat map, I put a couple of elements in it, and as you see here in the for loop, I get out the key and the value by calling this thing reverse view. I wrap reverse view around the flat map instance and then iterate over it and print out the key and the value. So that's one of the most powerful and amazing things is that we're actually extending all of the libraries that we already have that follow the conventions that we've had all along. So the range algorithms, as mentioned, are very much like the STL algorithms. And if you think deeply about algorithms for a minute, you'll realize that one of the properties of these algorithms is that when you call them, they execute immediately. There's no waiting. They execute exactly when they're called. And internal to the algorithm itself is where the iteration is called and controlled. So once you give up to the algorithm, it does its work, and you can see it. And as mentioned, these are not always a drop-in replacement, although what you'll see is that you can actually use iterators in most cases just the same way as you had in the past with the STL in the ranges version of them. Okay. So the views, besides being lazy, importantly do not own elements, which is the primary reason that collections are not views. And the important property here is that views are meant to be order 1 copy and assignable. So that means you can move them around in memory very quickly. And it means that you can pass them by value. You can pass them between processing phases and steps at very low cost. And this is also the thing that allows some of the infinite ranges. But the important thing here is actually, you'll notice about the views is that the iteration is no longer controlled by the view. That's what the laziness really means. It really just means that you, the programmer, will control the iteration over the view instead of having the algorithm do it for you. And then finally, as mentioned, we have a lot of cases where we want to transport a regular range, like a collection, into a view itself. And we can use range adapters to do that. And the range adapters also give us one other important facility. They allow us to create a piping syntax that is analogous in some ways to what you might see in Unix piping. It's not exactly the same, but the analogy is there. And as mentioned, these are declared in ranges views. Okay, so let's look at some more examples. So this one comes from CMC STL2. I could have used any of the other ones as well. So I have a standard vector. I have a predicate that checks if the values are even. In this case, I construct the view called evens, and you'll note I pass in the vector to the constructor with the predicate. And at the point of construction, no computation is occurring. Okay, it's only constructing the object itself. And I have to iterate over it. So here's the for loop. It's a range for loop. I get the integers back out and print them. Pretty straightforward, extremely elegant piece of code. So I can write this a different way. I have the same vector here, and I have the same is-even predicate. In this case, I don't construct it on the stack at all. I just make it the expression to the for loop itself. And that's a very nice way to write the same code. And now I can use an adapter. So if you were paying close attention, oops, not that arrow. Sorry. If you were paying close attention to this, you would have noted it's ranges : filter view. So the underscore view is attached to the name there. But here you'll see I have a pipeline, and I have ranges : views filter. So in this case, I'm actually using an adapter to create the view in conjunction with the vector itself. And this code operates exactly the same as the prior. So what if I had to write this with an algorithm? More than likely, I would have ended up doing something like this with for each, and I would have probably combined the predicate and the printing, which really makes my code less modular. But one of the things you're going to see here is that these are very composable. So the views are composable and the adapters are composable, whereas the algorithms were never terribly composable. Okay. So I think we've already said all this, but this is what's in the standard, and I thought it was particularly clear. Views are ranges, but they're special kind of range. So you can go reread that later on. Okay. Loops. All right. Let's do another poll of the audience. Who doesn't write any for loops in their code? Oh my. That was the null set. Okay. So I guess I won't get in too much trouble, even though I'm not following Sean Parent's guidelines. So, but, you know, I guess this is a question, right? Here we have the range for loop, which was really made for ranges, actually. It was an earlier proposal, and it happened in C++17 when ranges were already in the pipeline to be coming. And yet again, in C++20, the range for loop is being improved. So that first part, that init statement optional, is very much like the if optional init statement in C++17, and it's an enhancement. So has the committee really gone crazy? You know, they decided they were never going to listen to Sean Parent. Well, I think from a practical point of view, people are going to write for loops, and it's an improvement to have additional facilities to write them well. And I think I'm going to argue that in a lot of cases with range code, the for loop is not really so bad. But let's say that we do want to follow the advice. We can solve that problem. There's nothing that says that you cannot use algorithms and views together. You absolutely can use them together. So in this case, I have a print lambda, I have my predicate for is even, my vector again, and in this case, I've created a view called drop while using an adapter, and it takes the predicate, and I use the for each algorithm to iterate and make the iteration happen, and I pass the print in. So you can adhere to the guideline of no raw loops if you want to. I think it's also the case, it would be fair to say that you'll see in the wild when you start looking at range examples, this isn't uncommon that something like a for each and an algorithm would be paired together with a view. Okay, so let's talk a little bit more in detail. So we've already said that some of them are better. So there's the rough cheat sheet. I'm not sure that's quite on the screen. It's a lot of algorithms. But it's not all of the algorithms that you have today in the STL. Particularly missing are things like accumulate and some of the numeric related algorithms. And if you're interested in that subject, having range algorithms for those kinds of things, please see myself or Chris DeBella afterwards, who's also sitting up here in the front row, because he's working on that topic for C++23. So, should we go through all of these? Is this to be the Jonathan Bocera 105 algorithms? And no, I don't think so. But let's look at a couple more. And again, I think there's nothing mysterious about this at all. These are easy to understand. The for each we've already seen an example of. The count on the second line is an example. Again, all you're really losing there is the begin and end on the count algorithm. Is sorted is another standard algorithm today. And again, the only difference is you're losing the begin and the end. Oh, and this example, which I forgot to fix. But in any case, so here's a min-max example. So in the first part, I'm finding the iterator to the min element. So again, what we're seeing here is that all of the iterators do not disappear with the algorithms because several of the algorithms will return an iterator, and of course you'll need to check against the end before you dereference. And that's what the problem with the min-max is. Probably should have been checking that before printing them out. Okay, let's look at another one, copyif. Again, very much the same as a standard algorithm today. You have a copyif, you pass it the vector, that's the range that it gets, and then you use the range back inserter. So the theme that you're seeing here is that the things that you've seen in STL for 20 years are still there. They're in a new namespace, but they operate very much the same. And once again here, we're doing a copy into the v underscore CPY vector, and then we're printing it out. So I already showed you one sort at the beginning. Here's another sort. And like the STL algorithms, there's a lot more overloads than I'm showing you. And I'm actually not going to show you all of the overloads. They're extensive. But in the second example there with the deck, what's going on is I've created a function, reverse compare, and when I'm calling the sort, I'll have it compare in the reverse order, and I'll end up sorted backwards in that particular case. And now I have to say that I lied. Does anybody see a problem here? Not the front row. I can't hear you. Sorry. So the problem is that list is not sortable, right? Because it doesn't meet the requirements of the algorithm, right? So if you've ever tried to sort standard list in the STL, you'll get an error. And so what I told you is I wouldn't show you something that didn't compile, but I just showed you something that actually doesn't compile. And I mention it in part because one of the things that I think should happen, and I should have actually done this, but the problem is we don't really have a fully conceptified compiler at this point, but we should get a nicer error out of that sort that tells us something about, the list does not meet the requirements of the algorithm instead of, a horrible failure that has 100 pages of error message. Okay. So we're still talking about algorithms. And one of the interesting things that's been added to many of the algorithms in the ranges library is projection parameters. So projections give you a first-class way of getting at the object before it's sent to the predicate, for example, in something like a for each algorithm. So this really started with the Adobe source libraries, the ASL. So if you saw Sean Parent's talk earlier, he was involved in the creation of that. And this concept has been around, but it couldn't really go into the STL as it stood because it would be a breaking change in many cases. So here's an example of how it looks. Let's say that we have a structure like stuff. And what we really want to do is we want to sort it only by the IDX. We don't really want to use both. So one of the problems you can see when you get into something like aggregate types is you really only get one opportunity to write the equal, less, and so forth. But you might want to sort in many different ways. Now, I've shown it here where I have a little lambda that's the projection parameter. That's the third parameter to the sort. And it's just simply returning the IDX value. But you could call a member function and do other things that would return the value that you actually want to sort on. And so in that case, you can get different sort behaviors for the same type. And you don't actually have to write your own less or your own comparison operations in those cases. Okay. Is everyone still here? Has everyone had enough coffee to be awake? All right. So let's talk about views in some detail. So I'm going to spend the rest of the talk mostly on views and view adapters. Because as mentioned before, I think this is where you're going to get the most benefit. So before I was showing you different ways that you can actually write adapters and write code, and I was showing you the pipe operator versus construction and so forth. So if you dig into the standard, you'll see this little bit of information. It says an adapter constructed from a range and a list of arguments is equivalent to an adapter with a set of arguments in a range, or a range piped to an adapter with a set of arguments. Those are all equivalent ways to write the same code. And I have to say, the first time I encountered ranges, this went completely over my head. I had no idea. So let's look at a little bit more complicated case. So I have the vector of int again, and I have a predicate called even, and then a lambda that will actually square the value of the input. And so in the top loop here, we have a for, and we have the vector of int piped to an adapter for the filter of even, and then transform of square. So everyone knows what that code does, right? It's very easy to understand what it does. So it actually does exactly what you think. It goes through, and for all the even values, it squares them and outputs them. And we're going to actually trace through that example in a second, just to see what's really going on under that piping operator, so that you can feel comfortable that it's doing what you expect. But if you want to convince yourself that the two things from the last slide, or at least some of the things from the last slide, are the case, you can do this if range is equal below. And if you'll note, the first parameter to the range is equal is the vector of int piped to the filter. And the second is the filter constructed with the vector of int and the even. Oops. So, it's this in code. And indeed, if you run this code, you will find out that the two views that are created by the pipe operator versus the construction are exactly the same. So it's two different ways to write that exact same code. And this is one of the flexibilities that the range library is going to give you. There's multiple ways to express what you're attempting to do. All right. So there are no free abstractions, right? So the first thing I want to know is, yeah, sure, what's actually happening? How many times are we actually calling transform? Any guesses? Yeah. Shout it. 3. Correct. So this does exactly what you do. So I've annotated the lambdas to print out either EV when it's in the even or square. And if you run this program, what you'll see is exactly what you expect. Even is called 6 times. Square is called 3 times. And you drop into the for loop exactly 3 times. Now, I will tell you, this is not always the case. If you remember that views have these properties of being copied to cheap to copy and so forth, in general, views do not cache. So there are circumstances where you may be surprised by how many times something executes in a pipeline because there is no caching going on. In this particular simple case, it works. So now what would happen if I took this same bit of code and I put the transform first? Well, the obvious thing would happen. We would call transform a bunch of times that we don't need to. Okay. So now I want to look even further under the hood. And to do that, I have to get a little bit clever. I'm sure somebody has showed this at this conference. This is a function which allows you to print out the type of something in your program. This particular version of this thing is GCC specific. There's a Stack Overflow link there if you want to find out how to do this. But it's nifty. So the question is, what is all of this machinery actually generating in terms of types in my program? So in this particular case, I have the vector event, or vector string, sorry, at the top. And I use that type name thing I just showed you with decal type of the vector of string. And it prints out in simplified form. I simplified it a little bit for the slide. Exactly what you expect, vector string of Chock. So next, when I wrap a join view around it, and I get the type name of it, what do I get? I get join view of ref view of vector of basic string of Chock. Interesting. Where'd that ref view thing come from? So the ref view is part of the machinery of the library, and it's part of what gets wrapped around. And then you'll see below with take view, once again, I've wrapped that around the join view, and I'm building up a string of types that are wrapped around each other. So what you're doing when you're chaining things together is you're actually building a type. And that type knows how to execute the computation that you're trying to perform. So it's clever. Okay. Any questions? All right, let's talk a little bit about string view and span. And then I'm going to show you the rest of the views that are going to be in C++20, or a big chunk of them anyway, and some examples. So string view and span aren't really technically part of the ranges proposal, but they are range types in the sense that they're really there to interoperate. And they satisfy a contiguous range concept, which we didn't talk about the concepts, but a contiguous range is exactly what you think. It's laid out contiguously in memory. So that allows you to have high performance for many operations. So the string view, of course, is from C++17. it works with strings, and I'm not really going to talk about it further other than to say that obviously it works perfectly with these, It works well with views and range algorithms in general. But I will talk for a minute about span because it is new. And span is a template in a new header called span. And it takes a parameter t, so it's a span of a certain type. And again, to be satisfying view type behavior, it has to be cheap to copy. So it's really a pointer in size, 2 pointers, and it has constant time complexity for all of its methods. So not just copy and assign. It's also able to run during compile time evaluation as const expert, and it does actually allow you to modify types, which is unique compared to most of the views I'm going to show you otherwise. So here's how you can construct one. I have vector of int again, and I can construct a span of int from that vector. That looks range-like already, in a way. And then I have an array of 5 integers, which I can wrap a span around. And I also have a C array, which is interesting, which I can wrap a span around. So now I might be able to do something like this. I can pass the span as a parameter to a function that I write called print reverse. And that uses the reverse view, which is one of the views in C++20, to simply iterate over in reverse and print them out. So in the first call here, I pass the whole vector of int. You'll note I didn't construct a span anywhere. That just constructed automatically for me. So that's nice. It was an implicit construction. In the bottom two, I'm using the first and the last to subset the range of the vector itself. So that's another reason why you might use a span. You want to take part of it. So the span has a lot of other collection-like interfaces. Obviously, to support ranges, it has begin and end, but it has a number of other capabilities as well. All right, so that is a handy type that you might find. One thing to be aware of course, is you're giving out a reference to your collection, so make sure the lifetime of your collection is maintained. Okay. So, here's a cheat sheet. These divisions, by the way, modifiers and sampling and whatever, those are just my idea. You can decide whether you like them or not. We're not going to quite go through all of them, but we'll go through a few of them. Here's an example with iota view. Just like the iota algorithm. In this case, we've constructed it right in the expression, and we get the open range from 1 to 5, which is 1, 2, 3, 4. Here's take view. So, yes. Can you come up to the mic? That's probably the best way.
That wasn't a range for loop? That was just a regular for loop? Or it wasn't a stood ranges for loop?
Yeah. If I can go back up.
Yeah.
I mean, it's a range for loop.
Okay, I guess I thought there was a understood ranges. There was another stood namespace ranges for loop as opposed to a range.
No, there's nothing different about the range for loop. So the range for loop was actually introduced in C++17, and it has that colon syntax. And you'll see in a lot of presentations, you'll see stuff like auto-ref, as the supposed preferred way to access the values one at a time. Okay, I think the main differentiator there, right, is that colon is the indicator to you that it's a range for loop. Okay, so take view, and again, a little variation on the construction, but take view is essentially going to give you a finite number of elements from a range. So in this case, we're going to take 2 elements from the range. And you can see you can also construct via assignment. That's another thing, because remember, assignment, copy, all of these things are cheap. And then we can also say ranges, take view. Ooh, interesting, right? What happens if I specify something that's larger than the size of the range? It turns out it actually does the right thing. It will only iterate over the elements up to the point of the size. So another new one is join view. This is a way to flatten things out. So this one is very simple and straightforward, I suppose. What's interesting here, and in probably the next one, you're going to see we're actually doing this at the character level. And that has to do with the way the join view flattens things out. There's transform view. I already showed you one of these as well. So again, I'm just taking a random and iterating through. And again, important point, the underlying vector, if I printed it out, has not been modified or molested in any way here. All right, so let's combine a couple in a chain. So I have my isEven predicate, I have a print, and I have constructed from adapters this time, right? So after leading evens with a range view drop while, that's an adapter, and the take. So if we went back a couple slides to the take, you notice there's two constructor parameters in all of these cases, right? And again, that's that I can construct a view several different ways. In this case, I'm constructing the actual view type directly, and in this case, we're actually using range adapters, and it's the equivalent. Okay, and this time I'm using the for each algorithm to print out 3 and 4. Anybody know why it's just 3 and 4? And that's because drop while is going to just drop until the condition becomes true, right? So it's going to drop the 6 and the 2 because they're even, and then it's going to print for 2 more, and you'll get 3 and 4 out of that. Another one is an iStream view. So if we want to iterate over an input stream, and in this case, we're basically parsing ints out of this string. Empty view is a special case that you might use in development of your own functions and own views. It would come in particularly handy in the case where you might have a branch of something that is reached a point where you have no useful results to return. So you would return an empty view, instead of something that actually has values in it. And single view is a very similar kind of thing. It has actually only a single value, and it is a weird view in that it actually contains said value. So it's the one view that's a little different. But again, you can see you just iterate normally and naturally. And then there's split view. So split view does the opposite. It allows you to pull things apart. So I have a string, which of course is the canonical string for a programming conference. And the split view with a value allows us to pull it apart. Now, one of the interesting things here is what actually happens, and I was showing you the chaining of types. We don't actually get strings back out of this. We actually have to drop down and get characters back out of this. And that's a little bit interesting and surprising. Okay. Everything I'm about to tell you about performance is entirely anecdotal, which is to say it's meaningless. So take it for what it's worth. So as I said, we've been using Range v3 in production for a couple of years now. And our experience is that we mostly use range algorithms, mostly because when we started, we didn't know how to use views. So we're gradually using more views. We've seen no measurable difference in compile time performance, but that's just us putting our finger in the wind and not noticing, perhaps. And one of the things that's here is in the current implementations, almost all of them have to emulate concepts in some way, which is a bit of nasty business with macros and other things that are not particularly fast at compile time. So it is possible that current range-heavy code would not compile particularly quickly, but as I said, at least in our case, we haven't seen any real problem. Yes?
Recent versions of Range v3 have a concepts enabled version now, and I've noticed about a 20% compile time performance improvement.
Okay, that's interesting. And CMC STL 2, I believe, has been doing that for a while. Sorry, what? 30%. That was Eric Niebler, for the record. Thank you, Eric. Okay. But even with the old bad version, it really isn't noticeable. From a runtime point of view, it's a similar kind of thing, but our applications are limited. We probably only deal with ranges of hundreds of thousands of things instead of millions of things in a typical day. But I have a little bit of a theory about this, and maybe Eric will confirm or deny, but I think the range algorithms themselves are going to basically be the same as the STL, although interestingly in DeVere's presentation right before this, he actually showed how the views were actually faster in a simple performance test. But look, we've been using things like boost range for a decade or more, the string algorithms, and really what the algorithms are doing here is just pulling out the begin and end. So there's really not a huge amount of difference conceptually there. And maybe it's just possible that with writing views, you're going to avoid naive copies and other things that you might accidentally do with algorithms. But we'll see how it goes. Okay, so when these slides go up, there should be a large number of resources for you. Here's the links to the implementations we've already talked about. Range v3, as of yesterday, the examples have been making progress. I know that the group from C++ Now, Library in a Week, we did end up contributing some, and I can see that Eric or somebody else has done some more work on it recently. I have a rather older thing that came from C++ Now, so we're doing range by example. So there's a bunch of examples there. Those are not tuned down to the C++ 20 ranges, but are against range v3 directly. Working drafts. If you'd like, you can read the one ranges paper. It's 226 pages of scintillating material that no doubt will put you to sleep quickly. But yeah. And now probably the best thing to really read is the latest working draft. You can go to that link and you can get a copy of it. Because additional algorithms since the one ranges proposal have gone in. And here's some of the new ones. Now I will say, I'm sure there's some fans of range v3 that will be disappointed. There's things like ranges 2, which did not get into C++ 20. The ranges, that should be really : 2. That allows you to take the result of your range view and create a new collection from it. Projections on algorithms, and a lot of this is going off the slide, but you can go learn all the details about it. The 2014 paper talks a lot about it. There was a recent Reddit conversation that I linked here, and Sean Parent's talks are always worth the time. And then some more videos and blogs. Chris, who's just stood up a minute ago, wrote a nice blog post a while back and so forth. And there's some links to the span resources. And that's just about it. So I think, my reflection on this is that ranges is a key building block for the future. And even if it was just getting rid of begin and end, we're going to see a lot nicer, cleaner, more interesting code. We didn't see all of range v3, which is a very large library, make it into C++20, but I think we saw the core, the kernel part that we need, to move things forward. So thank you. We have some time for questions. 3 minutes. Peter.
For a lot of, let's say, safety critical code and other things, dangling is one of the issues we cannot solve well in the type system so far in C++. And my question is, are the view adapters protected against binding, are protected against binding to a temporary? Because today it's very easy to create temporary containers with class template argument deduction, initializer list, and so on. And the question is, what happens?
It's a good question. I'm not 100% sure of the answer, but my guess is it's probably harder. Sorry, what was that? Okay, it says you can't form a view around an R value, so there you go. Yep.
So if views are still depend on the lifetime of the original container, if the container changes, for example, I said take 2, and in my first print I cleared it.
Yeah.
So what happens to the loop? Are they invalidated like iterators?
It's invalidated the same as iterators, yep.
It seems like there's been a lot of recent flack against ranges from the community. Similar to what happened when async was introduced in C++11.
Sure.
Do you feel that ranges are ready for prime time, or is there still a lot of evolution that needs to happen for them to be useful?
Yeah, I've read some of those posts, and my personal take on it is we're going to say, let's let perfect be the enemy of the good. And so, yes, I think ranges are totally ready for prime time a decade ago, if we would have had Eric's library a decade ago. But with concepts and with this initial set of libraries, absolutely, I think it's ready for prime time. So I think those things are misguided in the sense that you're still able to go write your own range light library if you want to. But in terms of being able to have standard algorithms evolve and have new views and other facilities in the language that we can build on, absolutely it was ready. Yeah.
Hey, thank you a lot for the examples and the code. A few questions. Is there a type erased range also part of the C++20?
I don't think so.
Okay,
Right? Type erased range? No.
I have another question. How does STD distance work for like filter range? No, for filter and probably not, but like for transform ranges that actually doesn't change the amount.
I think you should ask Tristan or Eric.
Okay. Yeah, thank you.
Because they're the implementers. Yeah.
So I noticed that under the list of resources, Boost was not included, since I know you're a Boost knowledgeable person.
Yes.
Do you know if there's intention to get ranges, the C++20 ranges into Boost?
I do not know of any movement to do so other than maybe tackling one of these implementers and convincing them that it would be worth their time to do so. Or alternatively, a group of motivated people going about and doing it. So I can see that there will be a group of people that will want ranges maybe before C++20 because they won't be able to upgrade to C++20 for a long extended period of time. So that's, I guess, a new thing for Boost, which is sort of supporting the legacy versions of things for a longer period of time. So, but I'm not aware of any movement to do so. Hopefully there will be one at some point. By the way, the other thing I think we absolutely need is we absolutely need, some extensions to ranges that aren't in 20. And Boost would be a wonderful place to have those as well, because many of us do use Boost and have it anyway, so it makes it easier for us to get that. So, yeah. Okay. I think we're out of time, but we can keep going as long as the room is available, so go ahead.
Can views be concatenated or appended to each other? For example, if you have a view that shows only numbers that are divisible by 3, and a different view that shows only numbers divisible by 4, and numbers that are divisible by 5, can you concatenate all those to get one view that would then only show numbers that are divisible by 3 and by 4 and by 5?
I think you would use join view to do that, probably.
Join?
Yeah. Okay. All right, thank you very much.